Okay. Okay. So in last week, we introduced the process of CMOS verification. So we introduced many process steps, and we will discuss the details in the rest of this semester. So, but today we'll begin from the material, especially the silicon, the property of silicons. And we will introduce the crystal growth and the wafer fab and properties. Okay, so a high quality single crystal silicon wafer are very important. And when we talk about the wafers, there's a couple of things we need to understand. Okay, the first is the diameters. So what's the size of the wafers that we use? And also the thickness. Okay, thickness is also very important because it will relate it to your robustness of the mechanical robustness. Okay, so especially if you want to thin down the wafers, everything, so you have to consider the thickness in the beginning. And also the flatness. Okay, it's very trivial. You can imagine that you need to have a very flat surface, like a mirror. Okay, and also we care about the mechanical defects, especially if you have any scratches on top of your wafers. And also this crystallographic defects, okay, like dislocation densities. And we'll talk about different defects later. And also the crystal orientations. Because since the silicon, the arrangement of the atom is three-dimensional, and when we process these wafers, we have to cut into different slices of wafers. So the way you cut it, the direction you cut it will create different orientation of your wafers. And also the quality, how many impurities in your wafers. And also what's the dopant type. Okay, and your density or your resistivity. Okay, it's also very important. And why we use silicon? Because it's very cheap. Okay, there are a lot of silicons in our world. And also, second, the silicon dioxide is very stable and is a very strong dielectric. And it's easy to grow in thermal process. I think that's the very unique properties of silicon, because other semiconductors, the interface between the semiconductor and the oxide, and its oxides usually is not very good. It has some defect densities between the interface. So that will cause the problem when you try to control the transistors, right? Especially the defect underneath your gate. And so for silicon and silicon dioxide forms a very stable and very good interface. And it's easy to grow in thermal process. So I think that's very important for why we use silicon in our CMOS IC. And also silicon, the band gap, okay, is at 1.1 eV. It provides a wide operation temperature range. Okay, if you have a very narrow band gap, like some compound semiconductors, the narrow band gap will cause you some problems, especially when you increase the temperature. You will increase, like your intrinsic concentration will increase, and like turn on voltage and the currents, it becomes very difficult to control. So you need to have like certain amount of band gap in order for you to control the device. Okay, so here listed some properties of silicons, like its atomic number 14 and the weight 28. I think most people know this. And also the melting point is like 1400 degrees C. Okay, and the thermal conductivity is not bad. Okay, and also here is some etching. Like you can use some solutions to etch, like this KOH, HF, and also you can use dry etch, like you create plasma. Okay, that will react with your silicon. And also, if you want to use CVD to grow the silicon, there are many precursors that can be easily found, like this, the family of this silane. Okay, so we will see there are three types or three quality labels of materials. Okay, the first one is single crystal, and the second one is polycrystalline, and the third one is amorphous. Okay, so in the semiconductors, usually we can divide the quality to these three categories. Okay, the first one, single crystal, refers to like your atoms arrangement are very periodic, and like here you can see here is a schematic figures, and underneath this is TN figures. Okay, you can see that, for example, there's a set of unicell. Okay, this they are arranged in a periodic pattern in 3 dimensions. Okay, so repeat X, Y, Z, and each unicell is identical to other unicells. Okay, and their orientation is also the same. Okay, and also this periodic order, it can last for long range through the entire crystals. So we can see that this over a large amount of area. Okay, the atoms are arranged periodically. Okay, and what is a polycrystalline? So if there are 2 or more identical crystals arranged randomly throughout the materials. Okay, and like for example here, the picture shows that, for example, in this area, you can see the atoms arranged periodically. Okay, and also in this area and this area. But throughout the entire materials, okay, they don't exist the same orientations. Okay, but each individual crystals, okay, they are in very good orders, but you know, they are like 3, 4, you know, this kind of area. We will say it forms a polycrystalline. Okay, and between these individual areas, there is a line we can see. We call it a grain boundary, and this grain boundary usually you will conduct currents and some leakage currents, especially, and which is not very good for polycrystalline. And the third one is amorphous. Okay, so basically, the atoms are very disordered. Okay, so you can see there's no, they are not arranged in a periodic way. And also the orientations and distance between atoms are random. Okay. So if we want to have our device process on the silicon wafers, we need to choose high quality, like single crystalline wafers. But sometimes, like last week, we say that sometimes we have to use CVD to grow the silicon material on top of your wafers. But if you don't control your temperature or the process condition very well, you won't grow a single crystal silicon. Sometimes you become a polycrystalline silicon. And sometimes if we just need like a polysilicon as the gate for local interconnect, that's fine. But sometimes you want to process like transistor channel on top of it, we need to choose a single crystal. Okay. And since we know that there are three types of crystal qualities, how can we determine these qualities? Okay. Sometimes the quality is determined when it is formed or grown or fabricated. Okay, so it's determined by the condition, for example, like the pressure, the temperatures, the environment, the chambers conditions. Everything will affect your quality of your wave material. Okay, so in order to grow a single crystal, so in the following slides, I'll show you that there are two ways to grow a single crystal. Okay. Okay, so here is the basic idea. If you want to grow a single crystal, we need to put a seed crystal of the desirable crystal structure. For example, the orientation, you choose like 111 crystal and you will grow 111 orientation. And we need to supply the molecules. Usually it's a liquid, it's like a melted silicon or in a gas form. Okay, so they can grow on the seed. And also we need to control the very clean chambers and control the temperature and pressures. Okay, so here are two ways to grow the single crystallized silicon. Okay, the first one is Zakharowski growth. This is Polish, it's very difficult to pronounce. Sometimes we just call it the CZ. And another is called Flozone growth, and we will call it FZ. So we will introduce these two methods later. And before that, we have to talk about the orientations. Okay, so here we introduce Miller index. Okay, so Miller index is a notation system in the crystallographies for planes in the crystal or Bravis lattice. And we will use a number to describe or to represent a certain direction or certain planes. Okay, so these certain planes, okay, we use three integers. Here we call it HKL. They are the Miller index. Okay, so sometimes they are written in. We use parentheses to describe these HKL numbers. Okay, and each index denotes a plane orthogonal to a direction HKL. Okay, in the basis of reciprocal lattice vectors. So what is reciprocal? We will talk about this later in the next page. But here you can notice that if we mention the direction of a plane, that direction is orthogonal to your plane. Okay, and by convention, we can choose native integers. We will write it in like a bar, okay, or like -3s, for example. Okay, so here we are going to show you that how can we determine this reciprocal lattice index by the physical orientations. Okay. For example, here we see this a crystal in the 3 dimensions. There's a lattice constant we call it A. Okay, lattice constant is A, and the 3 direction is I, J, K direction. For example, like X, Y, Z. But sometimes we are not orthogonal, like X. So we use I, J, K here because sometimes they will form like certain angles. Okay. But here the axis between 2 axes, the angle is 90 degrees. So it's easy for us to give an example here. Okay. So we have these 3 lattice constant A1, A2, and A3, and we take this. We find the intercept. Okay, intercept of the axis in terms of the lattice constants. And then we take the reciprocals of these numbers and to reduce it to 3 integers and having the same ratios. And the smallest 3 integer HKL is called the index of the plane. Okay, so basically there are 3 steps. Here I show you an example. Okay, so for example, for this pink plane, they have an intercept with your axis at this A and infinity. Okay, you can see this pink plane. It has an intercept with your x. Here is A00, but for y and z axis, the intercept is in infinities. Okay, so here we find the intercept first. So we can get 3 constants. For example, here is A and I and F and I and F. And the second step, we take the reciprocals of these numbers. Okay, so we take the reciprocals first. So it's 1 over A, 1 over infinity, 1 over infinity, which reduce to 1 over A and 0 and 0. Okay, and the third steps, we reduce to 3 integers having the same ratios. Okay, so we can multiply A for these 3 integers and become like 1, 0, 0. 0 times A is still 0. So now we have this plane, this 1, 0, 0 plane for this pink one. Okay, any questions? Okay, just follow the process step by step, and determine this plane. And for the yellow one, okay, so this is triangular one. It has 3 intercept with like this point A, 0, 0, A, 0, A, 0. So it has an intercept with 3 axes at A. Okay, so if we take reciprocal, is 1 over A, and we get times A for these 3 integers, and we get 1, 1, 1. So this yellow one is a 1, 1 plane. Okay, it's very easy, right? Like some elementary school student can understand this. Okay. Now here is the family of this plane. Like for example, this is 1, 0, 0. It's very similar to we just talked about, and this yellow one is 0, 1, 0 plane. The green one is 0, 0, 1 plane. So basically these 3s, you can see that they're very similar. If the lattice constant like A1 equals A2 equals A3, then well it's very difficult to determine. But these 3s basically they are the same, right? So sometimes we'll use a group curly parentheses, or like a big parenthesis to include all these planes to become a family, like 1, 0, 0. Okay. What I just said is mentioned here. Okay, we can use this curly parenthesis to denote the set of all planes that are equivalent to HKL by the symmetry of the lattice. If it looks very symmetric, so like these 6 planes, basically they are the same, so we can use this notation to include the set of all planes. Okay? Or we just talk about the planes, but sometimes we will talk about the directions, the crystal directions, not planes. And we will use this square bracket to denote a certain directions. And this direction is based on your plane, okay, and is on the direct lattice vectors instead of the reciprocal lattice. For example, you can see the pictures on the left-hand side. This pink plane is 100 plane, and we use these square brackets to denote the directions which is orthogonal to this plane. So we call it 100 here. See, this direction is orthogonal to this plane. Then this is 110 plane. Okay, let's see this middle figures. This one is 110 plane, and the directions is we use these square brackets to represent 110 directions. And similarly, this plane is 111 plane, and we use these directions to represent this a certain direction of 111 plane. Okay. And again, we can use a set denotation to include all the directions that are equivalent to this HKL. Okay, so we can use this. I don't know how to say this. 英文叫什么? Some kind of brackets, okay, like middle bracket or something. I forgot. 就是这种括号，它可以代表这个同样的这个方向哦，一样就是我们这个curly bracket 去表示这个特定的 plane。那我们一样可以用这一个这样一个括号呢，来表示这个square bracket 的这个方向。Okay. Okay, so right now we just understand the planes and the directions, how we denote certain planes and directions. Now we want to get into the details of how the silicon atoms arranged in these 3 dimensions. So before that, we can understand first that some simple crystal unit cells. Okay, so the idea or the concept of unit cell means that you can use this cell to duplicate or represent in 3 dimensions and form bulk materials. Okay, so here are 3 very common. Now we can find out in our crystal. The first one is cubic. Okay, it's very easy to understand, right? It's like a cubic. So we have atoms on the corners, and the middle one we call it body center cubic. It has an extra atom in the body, which is in the middle of these unit cells. So you can see that these red atoms that is in the middle of your body. And we call it BCC, body center cubic. Okay, and the third one is face center cubic, FCC. Okay, it has extra atoms on 6 faces. Okay, and the centers of these 6 faces. 1, 2, 3, 4, 5, 6. Okay. Okay, so if you have this basic idea, then we will talk about the silicon lattice or silicon unit cells. Okay. Silicon is a diamond cubic lattice or diamond structures. How can we form these diamond structures? Consider that we have this is FCC that we just learned, right? We have 6 extra atoms centered as 6 faces. Then, if we have 2 merged FCC in the beginning, right? And then we can move one of these FCC, like we can shift it a quarter lattice in 3 directions. Okay, like this one. Like we have 2 merged FCC, right? So it will look like this. These black balls and these white atoms, they are all FCC lattice. But consider that if this is your regions, and the one of these FCC just move a quarter lattice in 3 directions. Okay. So then we move this quarter lattice, and then you can form, for example, this white one originally is at the same position with this one. Okay, so now it moves quarter lattice in 3 directions. And then we form the covalent bond to the 4 nearest neighbors. Like this one, you can form two nearest atoms. Like this one, and this one. Okay? So there are 4 closest atoms to these white silicon atoms. Okay, and in these figures we use different colors to represent. I think it's more easy to understand. Like this white one is this red one, and the 4 closest atoms is this. We use these 4 blue atoms to represent the 4 closest silicon atoms. Okay, and this 1, 2, 3, 4. If you use a cubit to represent it, you will look like this. So this is your this red one, and it has 4 closest silicon atoms. So this form a diamond structures. Okay. Or you can see here we have 4 red atoms. Okay, very similar. So you consider this a simple cubit. In the center there's 1 silicon, and in the top corners you have 2 silicon atoms, and on the bottom, but the other corners we have another 2 silicon atoms. So okay, this is our basic unit cells for this our silicon. Okay. And if you want to calculate the densities, like how many atoms per centimeter cube. Okay, so since we have here. This. Here is our. We want to calculate how many atoms in this in these unit cells. So we have 8 corners. Okay. Wait. Let me see. We have 4 inside this qubit. So 4 completed atoms inside these cells. Okay. So there's 1, 2, 3, 4. Okay. This is 1, 2, 3, and 4. Okay. These 4. They are completed inside these cells. And at 8 corners we have 8 atoms. So they share 1/8 cells. So 1/8 times 8, like this is 8 corners. So equals to 1. Okay. And then at the faces we have 6. So 1, 2, 3, 4, 5, 6. Okay, we have 6 atoms, and they shared among 2 cells. So this equals to 3 atoms inside the cells. So the total number inside the cell is 4 plus 1 plus 3 is 8. Okay, so and also you can see the cell volume is like this, and the density. So here's the density. We can see this a lot in different. If you take the semiconductor device physics class, I believe you will use this number to calculate some maybe the concentration numbers in your materials. Okay. Okay. So we just understand. Okay, this the cells for the silicon, for our silicon materials, and things it just repeat periodically in 3 dimensions. So some properties they are generally isotropic, which means you cannot tell the difference along like 3 directions or along certain directions. These both properties are generally isotropic, which means they are the same in different directions because of you have a symmetric structures. Okay. For example, that the dopant diffusions. Okay, the dopant diffusions, like it diffuse in these bulk materials, it diffuse in 3 different directions, and they have the same diffusion constants in 3 different directions. Okay, unless that when you hit the surface or terminate your surface, sometimes the surface will play another role in your process. Okay. Okay, but however here, now we know that our real device are built near the surface. Okay, our channel is a surface channel. So actually the surface properties or the properties on your surface are very important. Okay. For example, as we just learned that in the 111 directions, it has the highest number of atoms per unit area, and 100 has the lowest. Okay. So this, if we check these plans, okay, the densities, if they are two different, for example, 111 and 100 planes. Basically, on this surface, they will create different properties. For example, like your oxidation rate will be different, your surface density will be different, and like you near the surface, the diffusion process will be different. Okay. So this is the unit cell that we just see that, but if you view this unit cell in 100 directions, we will see a plane like this. Okay, for example, we can see from these directions, then you see this 1, 1, and this you see the half here, and you have 4 inside completely, and yes, 1 is here, is on the back planes centered, and in your back planes, then you have these two, and this one is here. Okay, so this is that when we see these 100 directions, then okay, we will see, okay, the plane will look like this. For example, if you want to check in the 110 direction, you look like this. And if you check these 111 directions, it will look like this very hexagonal plane. Okay, and the planes 111, okay, they have the highest density. So if you want to grow materials, you will most easily to grow on this plane, and also your oxidation rate will be faster. Okay. And some mechanical properties like tensile strength will be highest for 111 directions. Okay, so these are all related to your surface density. If you terminate at this surface, okay, so if you process 111 wafers and process 100 wafers, okay, they are made very much different. For example, like right now we work like we call the third generation semiconductors, like gallium nitride. So gallium nitride can be grown on like silicon carbide with lattice mesh substrate, but if you want a cheaper substrate, you can grow on a high resistivity silicons. Like for example, like TSMC, they are working on this kind of power device. They grow gallium nitride on silicon. They can grow like a 12-inch silicon substrate, and they have to be grown on 111 because it's hexagonal. Because your gallium nitride is naturally has hexagonal structures, so it will be easier to grow gallium nitride on 111 than 100. Okay, so those are also very one of these properties that will affect either your material growth or your process or your device properties. Okay, but you have consider now you have a wafers. And how can you determine the orientations or the plans of these wafers? Okay, so sometimes we will use some cut or notch to represent this. Okay, for example, here this is 6-inch, this is 8-inch. We will use this flat. Okay, this flat is created by when we grow an ingot, then we can use some tools to cut this to create this flat surface, and then we cut it to different slices of silicon substrates. And either we use this flat or we use a notch here. So when you see this, you know that okay, this represent these 011 directions of this notch or this flat. Then we will understand that this surface, okay, Okay, along this surface is 100 surface. So next time we have the silicon wafers, then you want to know, okay, what's the orientation? Is this 111 or 100? Then you can check if it has certain notch or flat. Then you can guess, okay, it's probably it's a 100 plane. Okay, so usually we will have 100 plane to fabricate our CMOS because it will create a better silicon and silicon dioxide interface. Okay, but if you want to have like high current driving capabilities, we will fabricate some bipolar device, and we will fabricate 111 because it has higher atom densities and can provide higher current. And if you use some chemical to etch, if there's a defect or sometimes you create a certain defect, you can use this chemical to etch, then you will create pits on your surface. And different direction or different planes, they will give you different shapes of your pits. For example, this one looks like inverted pyramid structures. And for this 111 wafers, it's like another pyramid structures here. And this kind of etching, because different etching, they will attack different angles. So they have different etching rate along different directions. So you will form these periodic and naturally pyramid structures. And sometimes, like for when we process the solar cell, in the silicon solar cells, we try to increase more your solar energy. Try to increase the light. Try to get it into your material. We will create this kind of roughness on your surface. So if your solar cell, the surface is like a mirror, so most of light will be refracted. Right? So you will not get into your material and generate electricity. Okay, so we will use some like etching techniques to create this surface roughness, like this pyramid roughness, and then we will enhance the efficiency, because your light can now be bounced back and reflected more times and before getting to your materials. So this kind of etching techniques is very common in your solar cell industry. Okay, now we will talk about defects in crystal. Okay, so first of all, we have to understand that there's no perfect crystal. There are some defects or some imperfections in your crystal, and we can classify it as different types of defects, from like point defects, line defects, area defects, and volume defects. Okay. Then from the figures we show here, if we have a point defect, we use V or I to represent the point defects. Okay, so from now on, when you see V, it means a vacancy or missing silicon. And you see this capital I is interstitials or extra atoms. Okay, so sometimes in my previous experience, that at the end of semester, students will come and ask me, teacher, why is V? Why is I? I say, okay, it represents a point defect. Okay, so in the following weeks, we'll see V and I very often. Okay, so don't come to ask me, what is V, what is I? Okay. So they means a point defect. And for example, a missing silicon, it can be a defect. This vacancy, we use V to represent this. And this I means you insert an extra atoms between your lattice. That you have an atoms at a position that is not supposed to be there. Okay, so for example, you can between this lattice, or you can form a bond in your lattice, that here. Okay, and line defect is a dislocation due to high stress or rapid thermal gradients. So if you have a point defect in this bulk material, but you have many point defects, then you will form a line defect. Or at the edge of your area defect or plane defect, there's also a line or linear defects here. Okay. And what is dislocation? Dislocation, you can see from these figures that this plane, okay, is created by the staking fault. So you can imagine that you insert this plane from usually from some stress or from some thermal process, you'll create this kind of dislocations. Like you have atoms that form a bond originally with their nearby atoms, but for this plane, this extra planes, at the edge of this plane, these atoms, it forms a line defect because they don't have another silicon atoms to bond with. Okay. So sometimes we say this stacking fault. Okay. And how about volume defect? Okay. So if you have a lot of point defect, it can also form a volume defect. Or sometimes your dopant will precipitate, like you add up the you add the dopant at high temperature, for example during diffusion process. Then when you reduce the temperature back to room temperatures, sometimes the dopant will precipitate and they will aggregate and become a volume defect. Okay. Okay, so for example here, which means you have another dopant, and when they precipitate and aggregate together, they become a certain bulk area that is now belongs to the original silicon atoms. Okay, so we call this volume defects. Okay, so there are many types of defects that can exist in your crystal. Okay, and it can be created by processing steps. So we have to be careful we process to make this device. We try not to introduce more defects in your material. Okay, so I think we will begin from the point defects. Okay, and in the following chapters, we will see when we talk about impurity diffusion or eye implantation. The point defects will create, will play a certain amount role in your diffusion or implantation process, because they will enhance your diffusivity, or when you try to increase the temperature to anneal the material, you will see that your dopant will move with your defect, and that is creating some transient effect. And so the point defects, they are very critical. And okay, so there are different types of point defects. Vacancy, V, we just mentioned. We have interstitial defect. We use I to represent that. And we also have a Frankel defect. The Frankel defect is that you have atoms that eat vacancies from its, which means it move away from its own positions in the lattice and transfer to another interstitial position. Okay. And also we have the intrinsic defect. This involves the diffusion or implantation process. We introduce some foreign atoms into our materials. Okay, so here this is a vacancy of vacancy defect, and this is interstitial defect here, and this is substitutional defect, which means a dopant, and this is also a substitutional defect. And this is a Frankel pair, which means you have atoms originally is here, and they move away to here, and it forms a Frankel pair. Okay. Okay, so now we will introduce line defects. Okay, line defects, there are two types of line defect. The first one is the edge dislocation. Okay, and the second one is the screw dislocation. Okay, and as I just mentioned in the previous slides, and in edge dislocations is a line defect, and where an extra half plane of atom is introduced midway through the crystal and distorting nearby planes of atoms. Okay. But this line defect or edge dislocation can be moved if you apply some stress on this material, and you can see that the edge dislocation can move along your material and until you reach your grain boundaries. Okay, let's see these figures first. Here is the extra plane, and we have an edge dislocation here. So if we have a shear stress, here's the stress, and this is a slip plane, and originally you have an edge dislocation here on this plane A. Now if you continue to apply the stress, okay, so you can see this edge dislocation move from the plane A now to plane B, back to here. And then you continue to apply the stress until you reach the grain boundary or the edge here. Okay, so here now you have your dislocations. Okay, and the second one is a screw dislocation. Okay, screw dislocation is also very easy to imagine that. Consider this a crystal, right? And you can cut it along a plane, and then you can, but you don't need to cut it all the way, right? You into 2 parts. Just cut it halfway, and you can sleep. Like for example, your this top plate and your bottom plate on different directions. For example, we all have eat birthday cake, right? Anybody? They don't have the experience eating birthday cake, right? When you cut a cake, right? Sometimes cake you have different layers. You have pudding, you have fruit, you have butter, ice cream, or whatever inside your cake. Right? Sometimes when you cut it, you see that different layers they'll move, right, between each other. This is a screw dislocation. So next time you can talk to your mom. Hey mom, there's a screw dislocation. They'll say, you guys are crazy. Just a birthday cake. Okay. Now we have a figures to illustrate what I just said. Okay. Now if we cut this along this A, B, C, D plane here, and we cut it and we try to apply stress, like screw stress, and you can see this is the original position here. Okay, and here this red shit. Okay, this is the new position. So in between, in the process, you can see these atoms that begin to dislocate from its own original positions. Also, okay, you can see from these bottom figures. Then we will use the Burger's vectors to represent this stress, okay, or this dislocation. But we will not go into details on this. Okay, I think it's time for us to take a break. Okay, let's take a 10 minutes break.
哦，它消耗2个。